And here we go with help video number 2. Our second help video. I think it won't be number 2. It'll be like 134 or whatever. But this is our second help video over the density of Penny's lab. When we last left off, we had discussed how to calculate the density, and we did calculations for the pre-1982 pennies. How about the pennies that were dated 1983 or later? How do we find those densities? Let's take a look at the mass of the Group 1 1983 or older pennies. The mass of Group 1 was 12.456. After they dropped them in the graduated cylinder, the water went from 21 up to 23. That's a 2 milliliter displacement, so the volume of those pennies must be 2 milliliters. So we take 12.456 and we divide it by 2 milliliters because density is the amount of matter measured in mass divided by the volume. So we take 12.456 divided by 2, and we should get something around 6.2. Once again, why did we round it to 6.2? We kept two numbers, the 6 and the 2, because this number here that was measured only has two numbers. You're only allowed to keep the same number of numbers in your answer as the number used in the calculations that had the fewest. So this has two numbers, so we're only allowed to keep two. We continued on and did the same thing for the rest of these calculations. They started with one group of pennies and then they added a second group. The mass went from 12.46 up to 25.024. As we see right here. They dropped those pennies in the graduated cylinder. The water started at 21. It went up to about 25. As mentioned, this was very difficult to read. These numbers could be off by as much of a half a milliliter or so. That's a volume change of 4. So we put 4 on the bottom, mass on top, 25.024 divided by 4, that's around 6.3. Same thing for the remaining calculations. The mass of the Group 3, which had Group 1, Group 2, and Group 3 on the balance, was 37.538. The volume of those pennies, the displacement was about 6 milliliters. So we put 6 milliliters on the bottom, 37.538 on top. Divide 6 into 37.538, we get 6.3. Same thing here. More pennies were added. The mass went up to 50.033. The volume displacement was about 7.5. That's a 6.7. All of a sudden it was 6.2, 6.3, 6.3. It went up to 6.7. Notice the volume was 2.46. This one was read as 7.5 displacement. Had it been only read as 7, if it was closer to 7, this number would have been down around 6.3. So it went 2.46. Oh, I'm sorry. If it was read as 7.5 and it really was closer to 8, this number would have been lower. If this number went up a little bit, then this number would have gone down a little bit. Finally, the last group was put on, Group 5. Its mass was around 62,510. The volume displacement was believed to be around 9. That gave it 6.9. But again, we know that a small misreading of the volume will make these numbers seem like they're further apart than they need to be. It was difficult to read the volumes. So if the volume was done a different way, the displacement method works very well, but using a graduated cylinder that goes up by 1 milliliter at a time introduced error. Then we came to the density of the gold pennies. That was the final calculation, the density of the gold pennies. We see here in our data that the mass of the gold pennies was 30.72. Density is mass divided by volume. So we need to 32.72, the mass on top. The volume change here, the water was at 3, the pennies were dropped in, it went up to 34, so the pennies displaced 4 milliliters, which means the volume of the pennies is 4. An object displaces its own volume in water. So 4 goes on the bottom. 30.72 divided by 4 is about 7.7. So that's the density of the gold-colored pennies. With that number, we can now determine, are those pennies actually gold? And we'll do that later as we begin looking at our conclusion questions. Why do you suppose this experiment found the densities of both the pre-1982 and post-1983 pennies? I think if we look at these numbers, the post-1983 seem to be somewhere between 6.2 and 6.9 in its density. The 1982 or older pennies seem to be around 7.7. This is off a little bit, but most of them seem to be right around 7.7. So the densities here seem to be almost a whole gram per milliliter apart. Somewhere around a gram per milliliter apart. Maybe even a little bit more. And that leads us to believe, even with the difficulty of reading the volume misreadings might make a 0.5, 0.6, 0.7 change, maybe a little more in these density numbers, but it's not going to bring these 6.2s up to 7.7s. So even with the difficulty in reading the volumes, it looks like the density of the pre-1983 or the pre-1982 and post-1983s are different. When we look at those, what can we conclude? Looking at the average densities, do we think that the pre-1982 has the same composition as the post-1983? And based on the densities, it would seem that they have a different composition entirely. Which had the higher average density, pre-1982 or post-1983? Well, the pre-1982s were around 7.7s. The post-1983s were less than 7. So the density of the newer pennies, the 1983, was less than the density of the older pennies. What does that mean? What does that mean? We'll take a look here for just a second as we get to question number 4. Knowing that the post-1983 has a lower density than the pre-1982, and knowing that copper metal has a density of 8.93 and zinc is 7.14, it would lead us to believe that the older pennies must have had more copper in them because their densities were higher. The pennies that were produced in the mint after 1983 had a lower density, which means they must have had more zinc in them, since zinc has a lower density than copper. Looking at this little thing here that was taken from knowledge of the percentages of metals used in these alloys. Look here, the 1962 to 1982 mint was 95% copper, which has the higher density, 8.93, and that same thing only had 5% zinc, which has a density of 7.14. So the more copper you had in there, since copper has a higher density, the higher density that alloy should have. In 1983 and beyond, they switched the mint to be 97.6 zinc and 2.4% copper. They almost flip-flopped this. Why did they change these numbers so dramatically? I think we could say that because copper is a more expensive metal. It's a more valuable metal than zinc. So they were able to save copper by flip-flopping here and putting a lot more zinc in than copper. Interestingly enough, though, we would have expected the densities of these pennies to be somewhere between 7.1 and 8.9. Notice that the newer pennies that we saw, the post-1983, was 6. It was below 7. Why would that be? Is it because maybe they put a different metal in there? No, the alloy was copper and zinc. It was just due to the difficulty in reading the displacement of the cylinder. We still saw that the post-1983 had a lower density. It was just lower than it should be due to the difficulty of reading these things. Notice, it's kind of interesting to see, the original pennies were 100% copper. Then they started making bronze. Bronze is not copper and zinc. Bronze has some tin in it. So bronze is copper and tin. So they went to bronze. In 1857 to 1864, they started using nickel and copper, not tin. They continued with bronze again, and in 1943 we will see something very interesting about the pennies. They were steel. Steel is an alloy of iron, often alloyed iron, Fe, the symbol is Fe for iron from the word ferrum, alloyed with the element carbon to make steel. But they had steel pennies, and steel doesn't rust, iron does, but steel doesn't rust very easy. But they coated them with zinc, and we already know that when you coat pennies with zinc, they look very silvery. So why did they not put copper in those pennies? Why did they use steel? Because 1943, World War II was going on, and during World War II there was a need for that copper for the war effort. We continue on. In this lab, they kept adding more pennies. So they started with group 1, then they went to group 2, group 3, they kept adding more groups. Group 4, they kept adding more of the same kind of pennies. Why were they doing that? I think the experimenter was trying to show you that the densities did not change for one of the particular pennies. It did not change significantly. Really, it didn't change at all if we consider the error in reading the volume, but the densities remain constant. Take a look here. The density when they had 3 groups of pennies was 7.1. Most of the other ones were 7.7. That's because we thought the volume change was 6.5. If we misread that 6.5 and it was really just 6.0, the density of group 1, 2, and 3, the mass stayed the same, but if we read the graduated cylinder again, we might have had 6. That would have brought the group 3, 1, 2, and 3, the density to 7 and 7.7. 46,101 divided by 6 is 7.7. We go back up to our chart, that would have been 7777. That one would have changed to 77 if we didn't misread this. They would have all been 77. So for a given type of penny, the pre-1982s, which had the same percentages of copper and zinc in them, it didn't matter how many pennies we used, the densities should have all been about the same. That is a big conclusion that we can make. It doesn't matter how many you measure. It doesn't matter how much of the density you measure for a given substance, it would stay the same. Looking at some other data samples here. Does the density matter how many pennies? Assuming we had all 1982 or all post-1983 pennies, the same type of penny, does the density change? Well, group 1, the density was 7.7, right up here. Group 1 pennies. Mass was 12.456, the volume change was 2. 12.456 divided by 2, that's 7.7. For all 5 groups on there, the density was 7.7. It didn't change. Why? The volume went from 2 to 10. That increased by a factor of 5. So the volume went up 5 times. The mass went from 15 to 76, almost 77. That also increased 5 times. If the mass increases 5 times and the volume increases 5 times, the number on top got bigger by 5. The number on the bottom got bigger on 5. 5 divided by 5 cancels. It doesn't matter how much of a substance you determine the density of. Density stays the same.